Okay, today we're going to begin Lecture 108, Mesh Current Method for Circuit Analysis. This outline is just to help stay on track. The Mesh Current Method in circuit analysis works with a loop currents instead of branch currents as in the previous lesson. As you perhaps realize, a branch current is the actual current flowing through a branch. We will, like right through here, and this is the branch. We will observe these branch currents when we measure I1, I2, I3 currents using the QUCS current probes of the video 107, which was our last lesson. Loop currents are abstract or fictitious quantities that are used to make circuit analysis somewhat easier than it is with branch current method. The term mesh comes from the fact that the multi-loop circuit, these, when drawn out, resemble a wire mesh. And it's just like the circuit we were just looking at. We have R1, R2, R3, VDC1, VDC2. Now, in the branch current method, this node right here, we'd have I1 coming into it. We had I3 leaving and I2 leaving. And then we would use Kirchhoff's current law to make one of three equations, because we had three unknowns. We had to have, it was the third order of unknowns, and we did the three equations to find the three unknowns doing substitution. Here, we're going to apply a systematic method of mesh analysis to our circuit first. First thing we do is we draw the currents clockwise, like this, and that indicates the current, which way it's going, but it doesn't have to be the actual current. The number of current assignments must be sufficient to include current through all the components in the circuit. We have three steps that we need to follow. The first step, sum the resistances around the loop and multiply by the loop current. Step 2, subtract the common resistances times the adjacent loop current, and for you for R2. Third, set the terms in step 1 and 2 equal to the total source voltages in the loop. The sign of the source voltage is positive if the assigned loop current flows out of the positive terminal, and the sign is negative if the loop current flows into the positive terminal and out the negative. We will use determinants to solve the equation simultaneously for each loop, but you can also use substitution method to solve the equation as we did in the previous video. We have two unknowns, so we will use a second order determinant to solve for the unknowns. You can also have three unknowns and you use a third order determinant, but you'd have three equations. Applying Kirchhoff's law around each loop, we develop the following equations. Here I1 does go through R1, R2, and then I2 minus the R2, I2, which is the opposing loop 2 current. In loop 2, we have a negative R2, I1. That's the I1 loop current as this one. And then we have the R2 plus R3, I2. So you add the sum of the resistance times that internal current, series resistance. This will end up being a negative. So as we substitute, notice that we only need two equations to solve for the same type of circuit we used in the last lesson, which was the branch current method, which needed three equations. The last two equations follow a certain format, which can be used as a format to make the mesh current method easier. Assuming the lump component values that we have currently here, we make our two equations, which become equation 1, equation 2. For loop 1, it's 70 I1 plus negative 20 I2 equals 10. Negative 20 I1 plus 95 I2 equals a negative 5 for loop 2. We're using determinants. We're going to use PTC Math CAD. Here I did the math already. After this, we'll use PTC Math CAD, and I will show you how to do this with the software itself. But what we do, we're doing matrix algebra, determinants. We make our first matrix out of this right here, 70, negative 20. That's this for I1, negative 20, 95 for I2. We know there's columns for I2 and this column's for I1. So when we want to solve for I1, we're going to take these voltages here, the 10 and the negative 5, and place that right here, creating this matrix or determinant here. Of I1, so I1 equals this. We take this determinant, divide it into this determinant, resulting in I1 equals 0.136 amps. We do the same thing for I2. So we're going to solve for I2. So we're going to take these two values, plug those into here for I2, which will create this determinant. 70, negative 20, 10, minus 5. Solving that, it comes up with, we divide this is 150, negative 150, determinant I2. Divide it by the determinant of the basic matrix, and that becomes a negative 0.024. All right. Since I2 is the only current through R3, it is also the branch current IR3, but opposite in direction of IR2. Using Kirchhoff's current law to check our answer, we have I1 equals 0.136, I2 equals a negative 0.024, and I3 equals 0.16. Adding this together, our answer is 0. Remember that we negate I2. It's already negative. We put a negative in front of it. That changes it into a positive, making I2 positive. Then the equation is 0.136 plus 0.024 minus 0.16 equals 0. That proves our equation. Kirchhoff's current law works for us, and we know our answer is correct. We're now going to go into the PTC MathCAD, and I'll show you how to build this equations and use the internal functionings of the PTC MathCAD. There's also a tutorial for determinants right here at this link, which will be in the notes of our YouTube. Now let us build the circuit in QUCS and compare our results. But first, let's use the PTC MathCAD Prime to do our calculations. This will be fun. Do our determinants, and I'll show you how to construct the equations. Go over to your MathCAD icon, double click, it'll start up. Starting on my other screen, I'll bring it over. Here it is. Now I am doing my YouTube video with the entire screen. Okay, well, once we got PTC opened, I'm gonna show you how to build this right here and get the answers using PTC to check your answers. So first thing we want to do is create our base determinant. So we click on this, DET, Shift colon, come up to the insert matrix, which was, we opened this up and we're on the math tab. We come over to the matrices tables tab. This is like Excel if you want to make a table, and this is the insert a table, same thing. Here's our matrix operators, and then here is our matrix functions that we'll learn as we go along. Today we're just going to use the determinant. So we need to make a matrix. We need a 2x2 matrix because we got a second order determinant. Our values are right here. So let's put in 70, tab to negative 20, tab to negative 20, tab to 95. That's the main determinant, base determinant. We want I1, shift colon, insert a matrix, 2x2 again, second order determinant. and we want to enter these values here. Now remember, we're doing I1 column, so we substitute the voltages column, and for the I1 column, the variable we're solving for. So this becomes the I1 determinant. So we enter 10, tab to negative second one, which is negative 20, enter negative 20, tab, negative 5, tab, 95. Check, looks good. Go to I2, let's do I2. I2, shift colon. We want to, we have the little gray area. We want to enter a 2 by 2 matrix again, second order. We're substituting 10, the voltage values, into the I2 column, creating this matrix right here. So we enter 70, we tab, enter 10, tab, negative 20, tab, negative 5, and hit enter. So now we want to find a determinant. So we come over to here, and we'll go to the vector matrices functions, select determinant. We want the determinant of the base first. Put that right there. Hit the equal key, and there we got 6.25 times 10 to the third. So it's 6,250 ohms. That's what that equals. So now we need to know, we're going to solve for I1 first. So we take the determinant. Once again, go up here, get the determinant. I1 equals, hit the equal sign, 850 ohms. So what equals 850? These are ohms, but the voltages are in the column, so it doesn't actually equal ohms. It's the number is 6.25 times 10 to the third. Determinant 1 is 850. But now we want to find I1. I1 shift colon equals 850 divided by 6.25 times 10 up caret to the third power. Come down here, that says that equation good. Type I1 equals, and that's your current. And as we know from this equation, I1 equals 0.136. And we do that for I2, and then do it for and then we solve I3, because remember, I3 is actually equal to the current going in this loop, which is not the same current as this. This current here is L1 minus L2 current. So it's got two currents going through here. So this would be I1 minus I2 minus I3, which comes up to this equation currently. So I3 equals 0.16. I2 is a negative 0.024 because of opposing currents. If you think you can do that, finish that, go right ahead. And if you have any trouble, you can email me or ask me a question, and I'll help you construct the rest of it. That's it. Now for the QUCS. Okay, now it's time to start the QUCS simulator. We begin by opening up the QUCS. Double click on the batch file. Now we would go to new. We would name it. I've already created the project, but I named it Mesh Current Project. You would put that there, whatever name you want. Then you would select the document settings. I got the grid of 1. So I put 1 here, said okay. I'm going to select a frame. I like A5. Select A5. I would title it, enter who drew it, which Lab Rats Engineering, date, revision. Say okay. You get this right here. That I don't want this. I'm going to just delete it, discard it. I'm going to click this project and say open, or select open. It creates this database here for me. Here is my schematic. Double click it, brings this up. So I built this according to the paper that I'm using. I mean, this is just to help stay on track. This is a circuit we're building. This is a circuit we analyzed. So we need a VDC1, R1, R2, R3, VDC2 connected like this. Now in our equations, we don't have a ground here, but in the simulator, you need to have a ground to do the SPICE simulations. But you put such a large resistor, like 10 mega ohms or 1 mega ohm, and that keeps the current from flowing down in there. And so you get the same results as you do when you're calculating and don't have a ground there. Okay, so this is what we're following. So now the thing would be just to wire wrap our components. These are current probes. Well, I'll show you where we got all this. So our components, resistors are here. So we got 3 resistors, one for the ground. The ground right there. We need power supplies. Go to sources, 2 DC power supplies. Got those. Then we need the current probes to measure our current. Current probes right here. See, that's like before, it automatically numbers them. You hit escape or come up here and hit this arrow to deselect it. I don't want that, so I'll hit that again. Delete it. But now we're going to complete our wiring, the diagram. Remember, the trick to this is to zoom really far in on the components you want to connect. I'm going to connect R3 to probe 2. Up here, get the wire wrap connector. Click right there, left click, drag it over to do a 90-degree left click once again down to the probe. Left click, coming up here, deselect that. You can see that it didn't connect. So I'm going to zoom in even further onto it. This one, I tried to use the wire wrap tool, but this time I'm going to connect onto the component, the probe, and I'm going to use the cursor to align it, the cursory keys, to align the probe until it goes solid black. You don't want any red circle there. Excuse me. So that's completed. Go back to a 1-to-1 frame, and I'm going to sign off here now and wire wrap the whole circuit, and then we'll come back and we'll simulate the circuit. All right, now I got it wired up. There's no red circles on any of the connections at all. Very good. So now we're going to assign our components. So we open up. We want our components to be R1's 50, R2 is 20, R3 is 75, VDC1 is 10 volts, and VDC2 is 5 volts. Put that down there. We'll come over to R1, click on the component itself, right click, edit properties. This is going to be 10 volts. Call it V1. I guess we could call it VDC1, but I can't do the lowercase. I mean, subscript. VDC1, apply. Okay. Add a property here. PR1, I'll just call it I1. Apply. R1, properties. It's 50 ohms. Okay, that's good. We'll apply that. Now this current here is a little bit different than you would think. So that's a good question for you guys. In the lesson we say that I2 is equal to R3 because loop 2 is the same current as in this loop that's going through R3. But I2 is not the same as the loop current going through the I3 because you have I1 current opposing I2 current. And that is the reason why it's I3 equals I1 minus I2, if you're wondering. Okay, so that we can rename that, edit that as I1 minus I. See, I can't do the minus sign. So I say just call it I1 and I2. Okay. We'll apply. Oh, we'll just keep it as PR2. All right. So, okay. And then we got R3, edit those properties. R3 is 75 ohms. Apply. R2 and its properties. R2 is 20 ohms. Apply. Okay. This is edit properties. We're going to name that I3. Apply. This is going to become VDC2. And it is 5 volts. Apply. Say OK. So we're set up. One thing we have to do is add the DC simulation. Bring that down to there. Well, we got to make R4. Under R4, I make that 10 megohms. And M, capital M, is for megohm. I'll say OK. Now the simulator will work because it has a ground, so it can do its equations. But it won't affect the results of our currents. We go up here, hit the simulation key. Do an F5, see what was wrong with that. Simulation aborted. Okay, it was doing the simulation. All right. This is going to take a little longer than I thought. Let's just look at the properties here. Temperature, DC. So there's nothing we want to change here. We're just going to go with that. So we click that. All right. F5, no errors. Net list. Go back to our schematic. Now we want to see what the results were, so we need to insert a table. We want a tabular table. Bring that over to here. Where can I put it? Put it right here. So we want to see I1, I2, and then I2, I1 minus I2, or the combination of that. Apply, say OK. And there's our values. We'll get rid of that. Maybe make this smaller. I don't think so. But there's our results. And do they equal what we have? I1 equals 0.136, correct. I2 equals a negative 0.024. All right. So I3 is equal to 0.16, which is the current going through here, right here, which would be the loop 2 current. Now, the actual current here, the negative 0.024, is going to be the I3 minus I1, and that's the current going through here. But as we can see, all our currents equal to what we had calculated. And so everything's copacetic, and we're done. Hope you had a good time. Thanks. Don't forget to select subscribe and hit the like button if you enjoyed this video.